So something your book talks about in chapter 4 is called the photoelectric effect. And this was explained by Albert Einstein. It's actually what he got his Nobel Prize for, not E equals mc squared, the equation everybody seems to think of when they think of Einstein. And photoelectric effect, photo meaning light, electric referring to electrons, so there's a connection between light and electrons here. Okay, it was known for a long time that when light hits a metal, that electrons can be ejected from the metal. Okay, so this ejection of electrons from the metal is called the photoelectric effect. Einstein did not discover it, he explained what was going on. So before Einstein looked at the photoelectric effect, people thought that if you increase the intensity or brightness of the light, it would cause both a change, it would cause a change in both the number of electrons coming out of the light, coming off the metal, and it would increase their energy. And it turns out this wasn't true. If you increase the brightness of the light, you would get more electrons coming off, but their energy was not increased. So we've got only the number of electrons being increased with brighter light. Okay, so how to explain that? Well, at that time it was known that light traveled through space as a wave. And Einstein came up with this totally out of left field idea that proved to be right. He proposed that electrons behave as a wave when they're traveling through space, and that they behave as a particle when they interact with matter. So if the electrons are coming in and they're hitting the metal, they're acting as particles or pieces of light. But as they're traveling through space, say to get from the sun to the earth, they travel as waves. Okay, this idea that Einstein came up with after observing the photoelectric effect is called wave-particle duality. Okay, that light has two natures. Okay, and just doing a little bit of vocabulary here that I should have done in the beginning. A single piece of energy is called a quantum, and a piece or a particle of light is called a photon. Now, I'm not quite sure, since energy, we think of there's other types of energy, I guess, besides electromagnetic radiation. So that's why we have the difference between any energy being a quantum and light, something on the electromagnetic spectrum, being a photon, I guess. I don't really know. Okay, but what Einstein then said is, when you've got a photon and it's hitting the metal, you have one photon going in can shoot one electron out. It can boot one out. That one photon in is not going to make two electrons come out, or three. One in, one out. But, and this is the really important part, this caveat here, this warning, the light has to have enough energy to remove the electron. Turns out low energy light's not going to do anything. High energy light will. So if you have high energy light, such as blue light or purple light, you're going to have that light hit the metal, and when it does, an electron will come zooming off of there. If, on the other hand, you have low energy light, such as red light, and it hits the metal, no electrons are going to come out. Okay, so one photon in, one electron out, provided the photon has enough energy. So, we're concerned with this energy, the energy of this photon, or any photon. So Einstein used a relationship that was developed by Max Planck, which should be pronounced Max Planck, but everybody thinks that's very weird. And this expression was E equals h nu, where E is the energy of the photon, nu is the same nu you've seen before. It's the frequency. Whoops, I put wavelength. Frequency. Okay, nu is frequency, the frequency of light, and h is what's known as Planck's constant. 6.626 times 10 to the minus 34 joules times seconds. Your book uses 6.63 times 10 to the minus 34 joules times second. That's probably what I'm going to use. Now, you guys may already be acquainted with Planck's constant if you watched Stranger Things. In the last episode, second to the last episode of the last season, they had Dusty had to get in touch with Susie, his girlfriend, because they needed the value of Planck's constant to open or stop whatever was going on to keep the underground creatures from coming out. And Susie knew Planck's constant, and she saved the day, and so did Dustin. Dusty, Roger, you remember what she was? Dustin. Okay, my bad, Dustin. Okay, so we have E equals h nu, where it's assumed that you're going to remember Planck's constant, or write it down, 6.626 times 10 to the minus 34 joule seconds, or 6.63 times 10 to the minus 34 joules times seconds. You'll be given the frequency, you solve for the energy. Or I could give you the energy and I could ask you to solve for the frequency. You get two and solve for the third. If you have, this is for a single photon. If you have a mole of photons, like a mole of atoms, you're going to multiply by Planck's constant. So you have the energy of a mole of photons is h nu times Avogadro's number. And if only the wavelength is known, you can make this expression say E equals hc over lambda, because you know that nu is equal to c over lambda. And we've just made a substitution in of c over lambda for nu. Okay, so let's just look at a couple of equations. You're going to practice some of these and in class. Okay, so I want to find the energy of one photon whose frequency is 4.5 times 10 to the 11th hertz. I'm using the equation E equals h nu. I put in Planck's constant, 6.63 times 10 to the minus 34 joule seconds, and I multiply it by the frequency. And when I do that, I end up with 2.98 times 10 to the minus 22 joules. I switch the frequency from hertz to 1 over seconds so that you can see how the seconds are going to cancel here. Joules times seconds are on the top, 1 over seconds, so that means seconds are on the bottom, seconds cancel, and you're left with joules. If you have a mole of these same photons, we need to take the energy we calculated for a single photon and multiply that by Avogadro's number. So the energy of a mole is h nu, which we've already done. We're multiplying by Avogadro's number. So here's the energy of a single photon, that many joules, multiplied by Avogadro's number, 6.02 times 10 to the 23rd photons in 1 mole. And that gives us 179.01, way too many sig figs. Let's just call it 179 joules per mole. We're going to practice using this equation in class, and it's important, don't forget it. So you want to remember this guy, and that guy. There's 3 things underlined in red, as well as the value for Planck's constant. That's it.